Reinforcement learning session at ICAPS. I think reinforcement learning is part of, does squarely belong at ICAPS, sequential decision making. So the first talk is going to be foundations for restraining bolts, compelling, reinforcement learning with LTLf, LDLf, restraining specifications. And we're going to have they're going to tag team on this presentation. So.
Hi, so this is going to be a little bit entertaining, which is good given the time. So this paper is by me, Giuseppe and Giacomo, Marco Favorito, a student of mine that is over there, Luca Iocchi, who actually will give a part of this presentation because I'm going to stop in the middle, and Fabio Patrizi that's still in Rome. So I'm going to talk about restraining bolt. Okay, what are these restraining bolt? If you have seen Star Wars, you know. So it's a little device, this thing over here, that they put on the various robots, and reading from the Star Wars official site, a restraining bolt is a small cylindrical device that restricts droid's action when connected to its system. Droid's owner install restraining bolt to limit action to a set of desired behavior. Okay, this is not me, it's Star Wars. So what we want to study are exactly these restraining bolt. Can we put in a learning system a restraining bolt? But before we go, let's understand, however, what we are talking about. So restraining bolts are used to control, restrict agents' behavior. Restraining bolts are placed on different kinds of robot. Okay, so you have the same restraining bolt. One time is put on a certain robot, another time on another one. What it means? It means that the restraining bolt cannot rely on the internals of the robot because it has to be generic. And also, the robot here, called the agent, is not built to accept the restraining bolt. Remember that in Star Wars, restraining bolts are put by the pirates, right? So you would like to build a robot that are resistant to the restraining bolt. Okay, now why this concept is interesting? This concept is very interesting because it talks about two different representations of the world. So on the one hand, we have a representation of the world by the agent, okay? So the agent sees the world in a certain way, a certain sensor acts in a world in a certain way through its actions. And then we have the restraining bolt. The restraining bolt is actually built by a different authority, but it also has a view of the world, different from the one of the agent. It's a completely different representation. They didn't talk. The builder of the robot and the builder of the restraining bolt, they didn't talk on the phone to decide which representation to use. So it looks at different features, typically more high-level features, since they cannot talk about the system, but they need to talk about the world itself. So two different representations of the world. Now, are these representations related one to the other? Well, no. In what sense, no? As I told you, the two manufacturers didn't call on the phone, didn't have a call to decide what representation we're going to use. So they are related. However, they are related because they talk about the same world. Okay, so the glue between these two things is the world itself. Now the question is, but can restraining bolt exist at all? Now, I come from knowledge representation. In knowledge representation, I would have said no. If you don't have the mapping between the two representations, you cannot do it. So I study reinforcement learning, because instead, in reinforcement learning, you can have it without having a special representation. So our problem is this, formally. We have a learning agent. Okay, a learning agent is essentially an MDP, unknown with transition and rewards unknown. And then you have a restraining bolt. A restraining bolt is written in logic, okay, over a certain alphabet L, okay, a certain alphabet L, which is different from the feature used for building the state of the learning agent. So these are two different, distinct set of features. And you write LTLf formulas over this. So you write temporal constraints over these features, okay, over the L feature, the logical features, okay? And you can have many of them. You can write many formulas. Not only that, but you can assign a reward when a certain formula is satisfied. So, for example, I have a formula, eventually be at the door. If in your trace you eventually are at the door, you get the reward, okay? Things of this kind. And what we want to do, we want the learning agent to learn a non-Markovian policy. Cannot be a Markovian policy this time because it needs to get rewards over traces. So a non-Markovian policy that maximizes the expected cumulative reward. Let me give you some example. Actually, Luca is going to show this example in more detail, but for now I just want to see them very conceptually, very high level. So we have a learning agent. This is the breakout, the famous game in which you have to break the bricks. You have a learning agent, and the features of the learning agents are the position of the paddle, the ball, speed, position, and then the action is move the paddle. And the rewards, you get a reward if you hit a brick. Now the restraining bolt. The restraining bolt talks about the brick status. So it has the list of bricks, and if they are on and off, their position. Okay? And the restraining specification is this formula over here. And this formula over here essentially is saying, I want to break one column at the time. I don't want to break completely the second column if I have not broken the first column. It's actually expressed in LDLf, okay, linear dynamic logic over finite traces. Let me give you another example. This is Sapientino. This is a game for kids in Italy, very famous among kids. And you essentially have a little robot, this thing over here, and you see you have arrows on his head, okay? And with this arrow you can control the robot, and the feature is the robot position, and we have a variant in which we can also see the angle, what the robot is facing. And then we have action, go backward, forward, left, right, and then beep, okay? There is a central button where you beep. Rewards, negative rewards if you get out of the board. That's the only thing you have. Now, restraining features, I have each cell with a certain colors, and I have the notion of being beeped, okay? There's just happened a beep. And then my restraining specification is to visit the color in a certain order. Okay, I want to visit the colors in a certain order. My last example is the cocktail party robot. So here, this is a famous scenario in the cocktail party challenge. And so we have a robot, we are in a cocktail party, we are seated in a table, however, we are not moving around. We are sitting in a table, and this robot will take us drinks, okay? And so what are the features for the learning agent, the robot? So the robot pose, the location of the object, the location of the people, these are the things that he knows. The action, he can move around in the environment, he can grasp and deliver things. And then the rewards, he gets a reward every time that a certain task is completed. Now, restraining bolt. The restraining bolt has the following. It has identity of the people and age, and if they've received items or not. Now, notice that identity, face recognition, okay? Age, you go on the web and you check who this person is, okay? Don't tell to Facebook. Restraining bolt, you want to serve only one drink and one snack to each person, and you don't want to serve alcoholic to minors, okay? So you see this notion of minors, it doesn't even exist in the mind of the learning agent. It doesn't know what minor is. Okay, so building blocks, classical reinforcement learning, actually linear time logic over variant of finite traces, and some work on non-Markovian reward decision process where the rewards are given in this logic. And what this work tells us is essentially that every non-Markovian policy for one of these systems in which you have an LTL specification of the reward is equivalent to a Markovian policy over another MDP, which corresponds somehow, is built as the Cartesian product of the automaton of the formula and the original MDP. And we have guarantees of optimalities. Okay, so these are exactly the same thing, actually. Okay, and so out of this, we can essentially reduce this non-Markovian reinforcement learning. Now, reinforcement learning, we don't have the MDP anymore. It becomes unknown, but we can actually use this construction to build an MDP and do the reinforcement learning to the equivalent corresponding MDP. Okay, but this is not our problem, because in our problem, we have a learning agent and the robot and the restraining bolt that are separate. They have separate features, okay? So actually, you can refine this theorem saying that actually out of this problem, you can get an MDP with unknown transition and reward, okay, over a larger state space that is not the state of the original MDP, but is the state of the original MDP plus the set of possible state of the automaton corresponding to the formula, okay? And this is, you have to expect it if you are doing a Cartesian product somehow. However, there is one important, very crucial point in this list. L is not mentioned. So the features on which we build the LTL formula are not there. Okay, and now I switch to Luca.
Thank you. So, yes. So what is important now is understand how we can implement all this mechanism. And what is important is that we are in the reinforcement learning framework. So the agent does not need to know the transition function and the reward function. So assuming you have this learning agent here that can, for example, solve the breakout problem, that's quite easy. You can find it many implementations. So this agent here has the state of the word, has some reward, and learn the policy, can learn the policy. Now we want to attach to this agent the restraining bolt. Of course, we need some information. For sure, we'll have here that the restraining bolt will give to the agent additional rewards. That's not a problem. It's not a change of the agent because the agent can collect these rewards as much as they want. But we need one feature that we have to add. So our learning agent must be extended with this variable Q. So what is Q? Q is not necessary to be a representation of the LTL formula or a representation of the DFA that is generated by the formula. It just needs to be an encoding because the agent just needs to understand that two states in the formula are different. They don't need to know which are the states. They just need to know that they are different. So we just need an encoding of the bolt of the formula. And this is done by just an integer value because the formula will generate a finite automata, and so we can generate we can encode all the states of this finite automata with an integer value. So what we need to extend our agent in order to accept the restraining bolt is just to add an integer value in the representation of the state. And so that's it. What we do is that we took some agents that were able to play breakout or Sapientino with the normal case, and we added just this variable. And with this additional information, the agent now receives an encoding of the state of the LTL formula of the restraining bolt, and some additional rewards. In this way, this agent is the standard implementation with SATSA, so there is no specific implementation, is now able to solve these complex problems. So you will see more in the demo area. We have a demo set up, so you can see the actual agents running and some examples. Here I will show you just very quickly some results. Of course, this learning task is quite easy because it's standard reinforcement learning. There are some problems that are solved in a few minutes, some other problems that are solved in a few hours. It depends on the complexity. But what is nice is that we see how the modularity of the approach. So we see that the same restraining bolt, so the same set of specifications, can be applied to different robots. For example, here we have two versions of breakout, one in which the agent just moves, and so just bunch the ball, and another one in which the agent can also fire. So the fire is the action that can break the bricks without the ball. So the very same restraining bolt can be used to control these two different agents, and you will see in the demo that they will all fulfill the task of killing the bricks from left to right, but of course with a different policy, because one agent has a different set of actions. And the same here in Sapientino. We have two different models of the robot. One is omnidirectional, another one is differential drive. So here the state, the representation of the state of the two agents are different because the agent can do different things. But again, the same restraining bolt can be used to learn the same behavior. And what is also interesting is that when we switch to a completely different domain, which is Minecraft, so in Minecraft, the agent has to do some actions in a certain order, then you can have the same agents. So in this case, we have exactly the same agents that are playing the Sapientino game, so the agent can move and can do an action. And we attach to these agents a different restraining bolt, and now this agent can learn a completely different behavior to play a completely different game. So all these results shows that the restraining bolt and the agent are very decoupled, and they are just linked by this information about an encoding of the state. And you can combine differently bolts and agents and come up with a completely different behavior in something that can be learned very easily. Okay, so conclusions. Here we suggest some questions for you, but of course, if you have other questions, we are very happy to answer, both here and during the demo session. I think what is interesting and important to observe here is that, again, this separation of representation in the reinforcement learning framework is very valuable because it allows an actual decoupling of the agent implementation and the bolt implementation towards the goal of having bolts controlling agents for our tasks. Thank you.
You have questions?
Hi, thanks for the talk. So you know that in reinforcement learning, there are serious problems of reward hacking. That is that when you specify reward and then you run your favorite reinforcement learning algorithm, and the agent does something that you didn't expect to do, but maximizes reward. So coming from the area of reactive synthesis, where it is often very, very difficult to specify things in LTL, and it requires different a number of iterations until you get the correct specification. So I wonder if what do you find? What problems do you think that it could have? We could have if we want to specify restraining bolts in LTL or LTLf or LDLf, And we have to spend so many computational resources to train the agents, and then we don't have the expected reward because they do reward hacking, and we don't know if the reward hacking comes from the LTLf formula or the MDP itself. So have you thought about that, or have you experienced these reward hacking issues?
Yeah. So of course it depends on the complexity of the problem, and it depends very much on the interaction between the rewards that you get from the environment and the reward that you get from the bolt. So in one extreme case, and this is possible from some of this example, we can completely delete the rewards coming from the environment, consider only the rewards coming from the bolt. And in that case, the numerical value of the reward coming from the bolt is not very important. You can put 1, 100, whatever. Because at that point, what is really important is to achieve the formula. So in that case, we have tried some reward shaping function that can help the system to converge to that solution. Well, in general, we know that fixing a reward for having the agent to learn is difficult. But I think that here we are in a slightly better framework because at least we can give less importance to the numbers and more importance to the logical formulas.
Thanks.
Yeah, very quickly. So actually you were mentioning that. So you have like two sources of reward signal. I would expect that the optimal solution will depend qualitatively on the balance between these two. So what can you say about that?
Yeah, well, of course, the optimal solution is always based on the definition of the rewards that you have. So if the rewards are properly balanced, you will have the optimal solution. But as I said before, in these cases, I think most of the cases, we didn't consider the rewards for the word. I think that the rewards for the word were only negative. So it's only when the agent does something that is for sure completely bad, like exiting out of the grid and something like that. So for example, if you have only negative rewards coming from the word and only positive rewards coming from the bolt, then of course this problem doesn't happen.
All right, let's thank the speaker. Okay. So the next talk is going to be deep policies for width-based planning in pixel domains. And the speaker is going to be Miquel Junyent.
Thanks. Hi. Okay. Well, hi, I'm Miquel Junyent, and I'll be presenting deep policies for width-based planning in pixel domains. This is joint work with my advisors, Jonsson and Vicenç Gómez. So, reinforcement learning has experienced a huge success in the recent years. There are attractive benchmarks with high-dimensional state spaces, but these learning systems are not ready for the real world yet. They require millions of steps to learn, and therefore are used in simulation. Some of these simulations, such as the Atari benchmarks, allow to recover a previously visited state, but most planners require to know the state action model to be known, and therefore are not suitable for these simulators. In that case, Monte Carlo tree search is the de facto planning approach, but the state, it treats the state as a black box, and we know we can do better. So width-based methods do not require the dynamics of the environment, and therefore can be used with simulators. And we know that they achieve state-of-the-art performance by exploiting the structure of the states. However, they are poorly exploratory. Although there has been some work in that direction, they do not learn from experience and require a feature representation of the states. So in this work, we covered these three limitations by combining learning and planning. So let's review quickly iterated width. IW is a blind breadth-first search method that prunes the states that are not novel. And for that, it requires the states to be factored into a set of features. So the notion of novelty is as follows. A state S will be novel for width I if at least one tuple of features appear for the first time during the search, with the size of the tuple being at most I. So let's see an example for IW1. We start at the root state. We generate a new node. Since we haven't seen a value 1 for the first feature, we keep the node. The second one, we have already seen a value 1 for the first feature and zeros for the other two, so we need to prune it, and so on. Here we have seen a value 1 for the second feature, so we keep it. And for the last one, we have seen already all these values before, so we prune it. So now the complexity is exponential in I and independent of the size of the state space. So in 2015, Lipovetsky and co-authors extended the algorithm to work with simulators. They presented results in the Atari games using the internal game state RAM as features. So it works as follows. At each step, the planner is given a maximum amount of nodes that it can expand. And after iterated with has been completed, we compute we compute the cumulative reward of all nodes, and then select the action of the branch that leads to a highest cumulative reward. We execute this action and then start over again. An optional step is catching this subtree of the selected action. So last year, Banders and co-authors modified the algorithm by, instead of doing breadth first search, they generated whole branches by first selecting a node and then rolling out until a node is pruned. This achieves deeper rewards quicker, allowing for a smaller horizon, and it let them plan in almost real time. They still emulated the width notion by keeping track of feature depths. And they used pixel-based features, which are basically the colors in tiles and the relation in their spatial and temporal relation. So our method consists of basically two steps, planning and a learning step. In the planning step, we do rollout iterated with, but instead of selecting nodes randomly, we guide it with a policy estimate. Again, a step is taken using the action with highest cumulative reward, and this best action is also serving us as a target for our policy estimate. Then we keep the last n transitions, we sample a batch from this data set, and then perform a gradient descent step to improve our policy. We then use this policy again for the subsequent plans. So let's see the planning step. It consists of two functions, select and rollout. Let's see a quick example. We can see up there a novelty table and the neural network that will guide our plan. We start from the root node. We sample an action from the policy estimate. Since the successor for this action is not in the tree, we roll out and generate a successor, add features to the novelty table. Since this is novel, then we keep sampling actions. And we do that until we find a node that we have to prune because it's not novel. Then we start all over again, sample an action, we see if it's in the tree. Since it is, and it's still novel, then we keep sampling actions, rolling out until we have to prune. We do it again, sample action, roll out, etc. So the learning step is basically supervised learning on this action executed at each step. More precisely, we sample a batch from this data set and minimize the cross entropy between the deterministic target action and our policy estimate. This can be easily parallelized by having more than one actor performing look-aheads and having a shared neural network. So probably you've seen this reminds you all of AlphaZero, so let's see the differences. So in AlphaZero, we have a Monte Carlo tree search that is guided by a policy and a value estimate. The tree policy the target policy extracted from the plan is on visitation counts, how many times we've gone through each branch instead of from rewards. A step is taken sampling from this policy instead of using the best action. And at the end of the episode, we update our policy estimate with the target one extracted from the plan and our value estimate with the real win-loss score. And note that we have to do this at the end of the episode because we need to know whether the agent won or not. So we tested this in simple grid world environments with sparse rewards, where the agent in blue always starts at this position, needs to go pick the key in green, and then go to the door in red to reach the reward of +1. We also give a reward of -1 and end the episode if it touches a wall or after 200 steps. Since iterated with needs features, we define this simple set of features we call basic. That it's basically the position and the color at that position. So since we have a mapping from states to distribution over actions, we can use the latent space learned by our policy estimate to extract some features. So we look at the last hidden layer and see if the neuron is active or not to define our set of features. And we call this dynamic features. So here are some results. The dashed lines in blue and purple show the baseline. This is iterated without any learning in the normal version and the rollout version with the basic set of features. And we can see how our method in green and red improves on them, learning over time and reaching the reward of +1 in the end. We can also see how our approach outperforms AlphaZero, here shown in yellow. And surprisingly, there is similar performance, and here even better, for the extracted features version from the neural network compared to the one in red for the predefined one. In a more complex environment, we can see how AlphaZero fails to learn the task, while our method still reaches a reward of +1, although it takes a little bit more time. And we can see as well how the difference between the automatically extracted features and the ones predefined is, so the performance is similar. So we also tested this in this one-dimensional problem, a simple corridor where the agent needs to go pick the key and then come back through the same path. And this is naturally a problem with width 2, since we need to encode for the position and whether the agent has the key or not. So it's not surprising that before learning, our algorithm needs some steps, some planning steps to solve this task. But after learning, we observe that our algorithm can solve the task in one planning step from the very beginning. This means that PyIW can reduce the width of the problem by learning appropriate features. We also show here in yellow the visitation counts, the visited state, sorry, during one planning step before any learning. So we can see how PyIW reach more distant states than the Monte Carlo tree search approach. And this is because it takes advantage of this of the structure of the state. We also show results for the Atari games. We use dynamic features with a horizon of 100 nodes, and this takes in our machine around 1 second. And we compared it to previous approaches of IW and rollout IW for half a second and 32 seconds of budget. In bold, we see the one with the best performance, and in blue, our method outperforming the one with half a second. We observe similar performance with the versions of iterated with 32 seconds of budget, that is 30 times more budget than in our method, and also with predefined features. We observe similar performance with PyIW. So to conclude, we've presented a novel approach for interleaving planning and learning From a planning perspective, we add a guiding policy to IW to inform the planning. We circumvent the requirement of predefined features by extracting them from the neural network. And these features learned or extracted from the policy, we see that they can reduce the width of the problem in certain cases. Also, we show comparable results to previous methods with a budget 30 times smaller, and again, with these extracted features, automatically extracted. From a learning perspective, we've introduced a planner that acts as a teacher, performs efficient look-ahead, structured exploration, and outperforms AlphaZero in these sparse reward grid-like problems. So our current directions are how to deal with stochastic dynamics, and also how to encourage these learning features that reduce the width of a problem. Please check out our repository. Well, thanks for listening.
So we have time for questions. So I have a bunch of questions. So I'll get you started, and if you have some more, you can ask later. So let's see. So you were learning policies. Did you compare to just running the policy by itself without guiding search?
Yeah, we did in some preliminary versions, and it doesn't achieve the performance of using the planner guiding the policy. So yeah.
What was it, a lot worse, or?
In certain games, it was okay. In other games, it just didn't reach high distance rewards, maybe. Yeah, I don't have here some graphs, sorry, right. But we can. I can show you some later. Sure.
Hi. How would you expect your method would work, or how well, if your reward is not sparse?
Actually, the Atari games have a lot of games in there, right? I mean, with sparse reward, there are like, I don't know, maybe 8 or something like that. And we perform quite well in most of them. So in the end, it works well. And actually, for instance, in Montezuma Revenge, which is one of the most sparse reward one that you can have, we don't perform that well. So we are doing okay in most of the games, but there are still some that we have to look how to deal with that.
Okay, thanks.
Thanks for the talk. Have you looked at which kind of features do you learn and if they're meaningful?
Yes. On that corridor one, we have. And it's true that you can see some features that, for instance, when it reaches the key, then it deactivates or activates, and from then on it is like that. But it's not most of the features like that. And to see that effect, you need to wait for a lot so that the training curve, and it's performing well, but you still need to wait a lot to see that converging into that sense. And that is quite surprising still, because we are not encouraging that effect. We have seen that in this corridor, for instance, but in more complex problems it's difficult to tell. And of course, it doesn't solve in like a very complex problem in one step in one planning step.
Yeah. So I have a question. We have time for yours as well. So maybe the elephant in the room, or one elephant in the room, is you're beating AlphaZero, which has solved Go, solved chess, solved shogi. So what was the challenge to get AlphaZero to work for you?
Well, the challenge is basically tuning it. It has some parameters that are quite game dependent as well. That's one thing. Actually, we tuned it for one game and left the parameters more or less the same in the other similar games, let's say. That's one thing. And I think it doesn't work that well because here it's facing a complex environment just from the very beginning, instead of facing another agent that doesn't perform that well, winning it, and so on. In the self-play version that we all know it worked well.
So for the search algorithm, when you set the width, is that just a hyperparameter that you set when you're doing the search for the width? And
I didn't understand, sorry?
The width?
Yeah.
Is that just a hyperparameter that you use?
Well,
is
yeah,
that,
we
learned?
used only width 1 for our experiments. And also the previous work was done with width 1 as well.
Okay. And does it have to be width 1? Or is that just something that you tune during search?
Well, basically, so the algorithm will be, the complexity of the algorithm will be exponential on that width.
Mm-hmm.
So basically, if we didn't try to put it to higher widths, but then, of course, every planning step would take a lot more time.
Okay.
All right, so let's thank the speaker again. Should I? Yeah, so our next talk is going to be resource-constrained deep reinforcement learning, and Abhinav Bhatia is going to give the presentation.
Hello, audible? So good afternoon, everyone. I'm Abhinav, and thanks for introducing me. So I'm here to explain our work on resource-constrained deep reinforcement learning. It was done in collaboration with Professor Pradeep Varakantham and Professor Akshat Kumar at SMU. So let's start by looking at an example of what kind of problems we are trying to solve. So suppose you have a city. This is a map of Singapore. And you have limited number of ambulances. And you have base stations throughout the city where your ambulances are deployed. So you want to place your ambulances to these base stations in a way so that you maximize the number of incidents which are served in a bounded time. So you would want to place more ambulances in a place where there are more incidents. So to do that, you observe the incident heat map, which is typically constantly evolving with time. And sometimes there are some unpredictable events like big fire incidents or unexpected traffic jams or maybe terrorist incidents. So nevertheless, to account for these changing demand patterns, you want to constantly reallocate your ambulances. Apart from that, there are some constraints in these kind of environments. For example, you have limited number of ambulances, and you could have constraints like a particular base station cannot have more than 3 or 4 ambulances, or you could have some administrative restrictions like every base station must have at least 1 ambulance. So we looked at the ambulance allocation problem, which is going to be our reference problem for the rest of this presentation. There can also be the bike sharing problem, which we can solve, in which you have to place bikes at different docking stations. And you want to do that to make sure that when a customer arrives at a docking station, he does find a bike. So what's common in these problems? These are sequential decision-making problems, and the transition model is not known explicitly typically. Apart from that, the action space in these problems is typically very large and discrete. So if you have C resources, Hello? Okay. Right. So the action space, as I was saying, is very large, exponentially large in these kind of problems. If you have C resources and about n base stations, then you would have about C to the power n possibilities at every time step. And there are constraints on the action space as I described. So the existing reinforcement learning approaches typically are not designed to handle these many number of actions. For example, DQN for Atari handles about 10 actions. And they are typically not designed to handle constraints on the action space. However, there is some existing work. So in one work, the authors handle large discrete action spaces by switching to continuous action spaces, but they do not handle constraints. And in other work, they handle constraints in reinforcement learning for robotics using an idea called OpNet. We'll talk about that later. But the approach does not scale to city-level problems where we have about 100 dimensions, for example, in bike sharing. So our work is designed to scale to such city-level scales. And we propose 3 approaches to handle constraints, which have different trade-offs. So the most basic approach is the constraint projection approach. It is a penalty-based method. It has very broad scope. It's easy to implement, but the problem is that it might not guarantee that the constraints are satisfied. So it's theoretically unjustified. Also, it introduces a new hyperparameter. So that's not very interesting. Another approach we propose is called Constraint Softmax, which essentially works by introducing a differentiable constraints enforcing layer into the policy network. It's easy to implement because it's essentially a closed form expression. But it doesn't work in some cases. And the third approach, which I think is the most interesting approach, is called a propped layer. And like Constraint Softmax, this approach also works by introducing a differentiable constraints enforcing layer into the policy network. So it has all the nice properties, except that it is slightly trickier to implement. So Constraint Softmax and a prop layer are our main contributions. So let's begin with a quick revision of DPRL, which I guess I don't need to go into. So it's meant to solve MDPs, and in reinforcement learning, the MTB model is not known. So you have to learn by trial and error by interacting with the environment. And the main key insights behind DPRL is one is the temporal difference learning, and the other is using deep learning to generalize better. So let's look at the MDP model for the RECO-RL problems, as we call it. So if you have C resources, n base stations, and t time steps in the episode. And you get to observe the current allocation at time t, and you get to observe the latest demand pattern, that heat map you might remember. And your action space looks like an n-dimensional vector of integers, where the kth dimension specifies the number of resources you want to allocate to base station k. The transition function and the reward function is per domain. And there are constraints on the action space. So you have the global sum constraint, which says that the number of resources are constant. You have local minimum and maximum bounds on every base station. And you can also have hierarchical regional constraints. So once you have local min and maximum bound constraints and the sum constraint, you can recursively specify these local constraints at various regional levels to specify hierarchical constraints. For example, if you have these n base stations in a state, you might want to specify a kind of constraint which says that this city in this state can only have these many resources, and that city can only have these many resources. And similarly, you might want to specify these kind of constraints at district level as well. So in this presentation, we are going to focus on how to handle global sum constraint and the local min and max bound constraints, because once you have that, then you can use your solution module, you can nest it recursively to solve the hierarchical constraints as well. So we have 2 challenges, right? And the first challenge is how to handle large discrete action spaces. To do that, we convert to a continuous space. So that allocation vector becomes that by dividing by the total number of resources, which are 100 in this example. And the justification is that in these kind of problems, similar actions probably have similar values. We need to normalize the constraints as well. So the global sum constraint becomes 1 now. And after we have employed this conversion, we can use a continuous action space deep reinforcement learning method like DDPG and leverage the power of gradient descent to do our optimization. And once we have the optimal action in the continuous space, we can recover the best action in the discrete space by just multiplying with C and rounding off. So before we dive deep into these three approaches, let me give a quick background of DDPG by contrasting it with DQN, because I guess probably everyone knows DQN. So in DQN, you have a deep neural network which approximates Q values of each action given an input state, and your policy is simply to pick the best action in that state. You don't need a separate policy network. In DDPG, which is like a continuous version of DQN, you have a deep Q network which has a slightly different architecture. It gives you Q SA value given as, it takes as input the state and an action. And because of that, you need a separate actor network which learns to maximize the critic, that it learns to pick the greedy action. So here is the chain rule equation which says the same thing. So the first approach is the constraint projection method, which is a penalty-based method. So suppose X is the raw output of the neural network. We have an activation layer, a sigmoid activation layer, but that does not guarantee that Y will be feasible. So we train the actor network to make Y feasible by adding this penalty term in the actor's update equation weighted by the parameter lambda. Despite that, there is no guarantee that Y will be feasible. So Q of, and when that happens, when Y is not feasible, Q of SY is not even defined. It's practically defined, but it's not theoretically defined. So it's theoretically not justified. Moreover, we need to tune lambda for every domain, which is not an exciting thing. And if we want to take a step in the environment, we need the feasible action. And to do that, we can just find the nearest feasible action to Y using a quadratic program. In our second approach, we want to make it impossible for the actor network to output infeasible actions. And we want to do that in a differentiable way so that the actor continues to be part of the end-to-end backpropagation training. So this is the kind of architecture we want, and we want the CS layer there to be differentiable. So we realize that the traditional softmax expression can already handle global constraints. It's quite easy. So let me explain that in more detail. So if you have X as the raw output of the actor, you get an intermediate vector Y using the expression shown there. And every component of Y would be between 0 and 1. And you use this expression to get your Z. And this ensures that the summation of all components of Z would be equal to 1. Then we figured that we can improvise on this expression to enforce max bound constraints. How? So we add a positive constant epsilon to each component of Y in the numerator and denominator. And then we observe that the maximum of Zk would happen when Yk takes its maximum value, which is 1, and all the rest of Ys take their minimum value, which is 0. So you substitute these numbers into this expression, and you get a set of linear equations which you can solve to get the expression for epsilons. So this is how we can handle max bound constraints. And once we know how to enforce max bound constraints, we can handle the case when we have min constraints quite easily. We can simply allocate those minimum number of resources to the respective base stations, and then the problem becomes that of handling just the global sum constraint and the max constraints. So this is the ultimate expression to do everything. So this approach provides a nice closed form differentiable expression to handle the constraints, but the only problem is that it works only when all the epsilons come out to be greater than 0, which need not happen all the time. So the proof is in the paper why that is necessary. So this brings us to motivate our next approach. We begin by asking the question, what is the most general way of building a differentiable constraints enforcing layer? Can we use a quadratic program and somehow find a way to differentiate through that? So that is exactly what was done by people who did opt layer. They used the idea of opnet for robotics. So they used the implicit function theorem to differentiate through the quadratic program mapping. The only problem is that it does not scale to like 100 dimensions. The reason for that is because with this method, you need to solve a quadratic program for every forward pass and some expensive matrix inversions for every backward pass. So we need to do something else. So these are the key insights. So we observe that opt layer is too general, and we have specific kind of constraints for the kind of problems we are trying to solve. And more importantly, we observed that there is no need for Z to be the nearest feasible projection of Y. Sorry? Okay. It can be any differentiable feasible projection, and that would do the job. So this is the kind of architecture we want to design. We want our prop layer to do the job. So we propose a semi-closed form, semi-iterative projection method, which guarantees that the mapping will be feasible. It turns out that the way we do it, it gives an approximately nearest feasible solution. So that's why we call it approximately opt layer. And this method is very straightforward to differentiate through. So here's how it works. If X is the raw output of the active network, then first we calculate an intermediate Y vector using this expression. So it enforces the Y vector to respect just the bound constraints and nothing else. Then we look at that QP we saw earlier there and pretend that the bound constraints are not there. And when we do that, it turns out that it's very easy to solve that QP, and you can have a closed form expression to solve that quadratic program. So this is the expression for that, this expression Z. And after we have done this, and if it turns out that, that the Z vector respects both the bound constraints as well as the global sum constraint, then we are done. But in most cases, that would not happen. It would, the Z vector would violate the bound constraints. And when that happens, we can run the clamp and redistribute loop. So what we can do is we can clamp those components of Z which are violating the bound constraints to that respective bound constraint. And that would be the final value for those components. Then there are some remaining components. So what we can do is we can redistribute the remaining resources to those non-final base stations using the same formula. And then we can repeat until our vector Z satisfies all the constraints. So there's a guarantee, we show that in the paper, that, that this procedure is guaranteed to terminate with the feasible solution. So here is an animated example. On the x-axis, you have the base index. On the y-axis, you have the allocation. The red line is showing the minimum constraints, the minimum bound constraints, and the green line is showing the max bound constraints. So initially, so you start with an infeasible allocation, then you apply the formula, and some of the components go below this red line. Then you clamp them. That happen again. So you clamp them to the respective constraints, and then you redistribute again. And that's how you get a feasible solution. So what about the derivatives? So if a component was clamped during the loop, then it was assigned to a constant. So its derivative with respect to all the inputs would be simply 0. And if it was not clamped, if its value was computed using that expression, then that expression is quite trivial to differentiate, right? And so the derivative is simply del kj minus 1 upon n dash. N dash is the remaining number of indices which were not clamped. That del kj is the, I think it's called the canonical delta function, which is 1 when k equals j, and it's 0 when k is not equal to j. So we did our experiments on the ambulance domain and the bike sharing domain. On the ambulance domain, we considered two kinds, we had two variations of the domain. In one variation, the demand pattern was very simple. It was simply Poisson. That it means that the incident pattern was just a function of time. So it's more predictable, and it roughly matched the incident demand pattern in Singapore. And then we had a more interesting variation in which we introduced random surges. We wanted to do that to simulate catastrophic events. And we wanted to compare how classical approaches compare against our approaches. Like we want, right. So, and on the bike sharing domain, we had a real data set of a city. And it's already a quite nuanced data set. It's not Poisson. So we compare against the vehicle repositioning baseline. So when we did that, on the Poisson demand pattern, which is the more predictable one, we found that all three of our approaches did comparable against the baseline. And when we introduced some random surges, then the DDPG abrupt method did about 15% better than the other methods. And in the bike sharing domain, all our approaches did about 50% better than the baseline. So to conclude, a general approach like DPARL can be applied, and it can be comparative or better than some classical approaches. That's what we demonstrated. And we showed that reinforcement learning is especially valuable when the demand pattern is more nuanced than simple models like Poisson, because in such cases, a reactive policy is valuable. And we showed how to handle constraints at scale. We proposed 3 different approaches, and they have different trade-offs. So thank you. Any questions?
Questions? Yeah. So your final step, you convert to a continuous action space from a discrete space. And so finally, you have this discretization step.
Yes, that's true.
Is that taken into account anywhere, or is that just sort of an approximation?
Yeah, it's an approximation. Yeah. So you typically end up, so you find the optimal solution in the continuous space, and then you just multiply it by the total number of resources, and you just round off. So there are more interesting ways of rounding it off, and there's a paper on that. I think I referred the paper somewhere. So you can actually consider some 3-4 rounding off candidates which are nearest to that continuous solution. And then you can pick the one which has the best Q value. So there can be more interesting ways of doing that, but it turned out that we did not need it. Just the nearest rounded off solution by L1 norm did the job for us.
So any other questions? I guess I have one more. So you implied that you were solving sort of a canonical constraint problem, and that you could then recursively apply that?
Right.
Is it really just straightforward to do that, or are there other challenges involved?
Right, so I'll explain to you how to do that. I hope I can do that in 1 minute. If there's no more questions, I can, explain in 1 minute. I'll go back. Right. So once you have a module which can handle local constraints, so suppose that is your state. So suppose that's California, and you have these n base stations. So some of these 5 base stations, suppose, are in Berkeley, and you want to make sure that Berkeley gets maximum of 15 ambulances and a minimum of 10, say. And suppose that's Oakland, and it has its own constraints. So at the first level, you can have a differentiable constraints handling layer which can allocate the number of resources which need to be assigned to Berkeley and the number of resources which need to be assigned to Oakland. And then once you have the resources which need to be assigned to Berkeley, then at the district level, you can keep carrying out the same process. So you can build this computation graph by recursively nesting these modules.
All right, well, let's thank the speaker again.
Thank you.
Okay, so hello, I'm Pawel, and I'm going to talk about learning classical planning strategies with policy gradient, which is joint work with my supervisors at Imperial, Dalal and Alessandra. So first, a couple of words about the general setting we are in. So we are dealing with satisficing classical planning. This means that for most of the problems, it's challenging to find any solution. Of course, given that we have the solution, the lower its cost, the better. We also approach the problem with heuristic forward search, just like most modern satisficing classical planners. And given those assumptions, our problem is to construct a planner that interleaves between various search approaches in the process of solving a planning problem. And later, given that, we want to use reinforcement learning to discover search strategies, possibly tailored to a specific distribution of planning problems and a specific performance objective on which we intend to score the planner. So learning is, of course, not new in classical planning. Over the years, there has been a lot of work, including learning macro actions for planning, learning decision rules to control the search, learning heuristic functions to estimate the distance to the goal from any given state, and even automatic portfolio configuration. So to the best of our knowledge, this is pretty much the first attempt to use learning to discover search strategies that are then applied while solving a given planning problem. So similarly, searching with multiple algorithms has been present in literature in a number of ways. So one important body of work is on combining best first search with some auxiliary exploratory mechanisms. And this is a work that we draw a lot of inspiration from. However, there are some notable differences. So first of all, we don't constrain ourselves to two search mechanisms. We provide a number of them. And even more importantly, we don't specify by hand how to switch between various search approaches. We leave that decisions to the learner. Planning with multiple algorithms is also restarting search, like FF, which uses enforced hill climbing before falling back on best first search, like Llama that iteratively tries various weights for A star. And of course, when we are talking about running independent searches, we are only one step away from portfolio planners that potentially throw a myriad of potentially unrelated planning mechanisms at the problem at hand. So importantly, the difference between our work and the latter two here is that we are dealing with a single state space, a single search. We've got a single open list, and the problem is to decide how to process the current search frontier, what to do further with it. So at a very high level, an overview of our planning approach is while the problem is not solved, we choose one of the search routines that we've got available, and then we keep applying it for a fixed period of time, then choose again, potentially a different subroutine. And to make it a reinforcement learning task, we need to define a couple of entities. So first, we need some set of states. And in this work, we will generate the set of states by defining a set of variables describing the planner state. And then each possible assignment over those variables will constitute a single state. Similarly, we need a set of actions, and this will be our search routines. And we need to specify a reward, that is some way of scoring the planner performance. Assuming for now that we've got this set of states and set of actions, we can define a stochastic policy by just associating a single weight with each state action pair, and then the probability distribution over actions in any given state will be defined by softmax in the weights associated with that state. So this is a fairly standard tabular policy gradient approach. And when we have defined our policy like this, we can train it with a variation of reinforce algorithm, which applied to our problem updates the weights at every time step like this. So what we do is we average over n runs of the planner to reduce the variance of the gradient estimate. And then for each attempt to solve a problem, for each trace in reinforcement learning terms, we loop through all the possible state action pairs, and then proportionally to how often this state action pair occurs in the trace, and proportionally to how well, how high was the reward for that run compared to average for runs passing through that state. We update the weights according to the gradient of the policy, normalizing by the probability of the action to correct for the fact that some actions occur more often. So far, we've been keeping the state and action space very abstract. So now to ground it a little bit, we introduce a specific set of two state variables, two binary variables in this work, D and T. D is a binarized estimate of the distance to the goal as measured by the heuristic that we are using. So it's 0 if we are closer to the goal than to the starting point. It's 1 otherwise. Similarly, we use T to express how much time we've got remaining. And for simplicity and readability, we further refer to the states in S as either near, when D is 0, or far, and respectively early or late for T. Regarding the action space, we define 5 search routines. One is plain greedy best first search. The second is epsilon greedy best first search. So choosing the best state in the queue with probability of 1 minus epsilon and a completely random state from the queue otherwise. Another one is best first search, augmenting each state expansion with a number of random walks. Another is local search, starting a local search from the best state in the queue and then continuing it for as long as the action is applied. And the final one is heuristic guided depth first search. So that's depth first search with the tiny twist that since we are computing the value of the heuristic anyway to insert the state in the open list, we also use it to order successors of any given state for the purpose of depth first. And the final component we need is rewards. So we use 3 different ones to see how the policies change when the reward is different. The very first one is the IPC score that we all know and love in this community. So this is the quality of the cost of the best known plan over the cost of the plan returned by the planner under evaluation. One variation of this that we use is a squared IPC score. So we take the number and raise it to the power of 2. So intuitively, this increases the emphasis on the cost of the plan. So hypothetically, a planner returning a plan that's 2 times longer than the best known one now only gets a quarter of a point rather than a half. And something totally different, we also try a time reward. So we score the planner based on how much time of the allocated timeout was left unused. So this is something that's closely related to plain coverage in that it disregards the action costs, the plan costs, sorry. But in this case, it's even more extreme in the sense that it pushes the planner to find a solution as fast as possible rather than just being satisfied with fitting within the time limit. And for evaluation of the resulting systems, we use 5 planning domains of the IPC 2014 learning track. So these were transport, parking elevators, no mystery, and floor tile. The only one we excluded is spanner, which was sort of designed not to work very well with the lead relaxation heuristics. And we are using fast forward heuristic through all the evaluation. We are using so-called 5-second problem distributions. We are looking for generator parameters such that more or less half of the problems can be solved by a baseline of a best first search with fast forward heuristic. So this is to make the problems not too easy, not too hard, challenging for the system that we have at hand. And these are the problems that we use for training. This is also where we do our primary evaluation, but also to see whether the learned policies are of any use outside the training distributions. We also take full-scale problems from IPC 2011, which, as far as I know, is the last one where these 5 domains occurred together in the satisficing track. So first, a couple of words, high level, about qualitatively what policies have we learned. So in general, the policies happen to be quite conservative for no mystery and floor tile. The learner was consistently choosing either greedy or epsilon greedy search. This is understandable if you look at the character of these domains. So aggressive exploration can be dangerous. You can end up in some undetected dead ends. Things are a little bit more interesting on logistics style domains like transport and elevators. In those domains, we can see the impact of different performance objectives of different states of the planner. So very typically, the planner would start more conservatively, but then under time pressure, when the time starts to run out, it switches to methods with more exploration, more depth bias. And on the other end of the spectrum, we've got parking, on which the learner actually chose to go consistently depth first and irrespective actually of the performance objective. And indeed, on this domain, or at least at the problem distribution that we have at hand, it turns out that you can do depth-first search without too much cost in terms of the plan quality. So these are the policies for elevators. We report all the policies in the paper. Here, for the time constraints, we only report arguably one of the more interesting ones. So on the left-hand side, we've got all the states, and then the table is divided into 3 sections for each of the rewards. And we can see the probabilities of taking each of the actions in each of the states considered. So for example, we can see that under the IPC reward, the search starts with random walks, then proceeds with either random walks or local search, and when it's really under time pressure, when it's still far from the goal and it's getting late, it actually goes for depth-first search. For comparison, under the time reward, the policy is very heavy at depth-first search all the time. So one important thing to note here is that not always when we see that the policy stays close to uniform, it doesn't always mean that the learner prefers to stick to the uniform policies. Some of these states just tend not to be visited in the training process very often. So this is, for example, the case for the far late state under the time reward, the very last row. If you start approaching the elevator's problem with depth-first search, then you're very unlikely to ever end in a far late state. So this is why there's just not enough training signal in that state, in that domain. And this is why it stays close to uniform. Now this is not necessarily a huge problem because in most reinforcement learning applications, you would hope that if a state isn't visited in the training phase, it will also be unlikely to be encountered under test conditions. So how well do these policies do? First on small problems, so held out test problems, but following the training distributions. And we compare against the baselines of each of the subroutines on its own, as well as a uniform policy, mixing all of them with a constant uniform probability. And then our free learners, primarily the one with IPC reward, so the same way of scoring it that we are reporting here, and also the other two. In the paper, we also reported all the 2 remaining scores. So we can see that the planner is competitive with the baselines. For every domain, it's either the best or close to the best, with the exception of no mystery, perhaps, where epsilon greedy does really well. And naturally, on aggregate, this leads to performance superior to any of the baselines. And now for larger problems, the policies are also potentially useful, also competitive, so that the difference isn't as pronounced here as you could expect. The sums are still best overall, but you can see that, for example, local search is also very competitive on aggregate. So to sum up, the contributions of this work are first a framework for alternating between various search approaches while solving a particular planning problem. Second, a way of using reinforcement learning to come up with search strategies tailored to a specific problem distribution. And lastly, we provide a first simple but quite effective instantiation of this framework. Of course, there is so much here that you can do in the future. So first, the representation of planar state that we are using here is very, very simple. In the future work, we would like to consider more complex state representations. There's so many more things that you can say about the state of your planner. For example, you could look at the distribution of the heuristic values in your open list. And of course, the more complex we go about the state representation, the more natural it will be to use some form of function approximation rather than the essentially tabular approach that we have at the moment. Another thing is you could extend the set of search routines. So it's not like you can fit anything in this framework, but there is a lot of things that you can. So for example, it would be quite exciting to see local search with a different heuristic, or perhaps novelty-based search as additional routines. And finally, we would like to consider continuous action spaces. So you can see that with each of these subroutines, we sort of introduce a lot of hidden parameters. So there's epsilon greedy, but what's the epsilon? There's random walks, but what's the length of the walks? These are all parameters that you could aspire to train. And at the moment, we are working on alternative parameterizations that would allow for this. Thank you.
Right. So any questions?
Hi, thank you. When you're comparing the basically your selection approach against the baselines, which test the individual search strategies, so what, on the test set, did you give any notion of training for the baselines, or were you just testing?
No, that was just testing. So under our framework, there was nothing really to train in the baseline.
Right. So I'm just wondering, do you think it could have been more fair comparison? Because maybe these individual search algorithms do have meta parameters that you can train. So now
okay, trying to train those parameters.
Yeah, because
it's because so I agree in a way. But on the other hand, all those parameters that we are talking about, we also keep them fixed for our learner. So definitely for this sort of next work that I'm mentioning here with continuous search spaces. So when we train those parameters for ourselves, we will definitely train them for the baselines as well.
I'm just talking fairness compares in context of just giving enough demonstration. So you're fair in terms of demonstration, but the learning approach is different. Yeah, but thanks.
Right. Anybody else? Yeah.
So I'm wondering if you can comment on the representation of the state of the planner. You could basically use the state of the state search space itself as a state. And I think some people have done this before. Here you reduce it into 2 bits, and whether there's a scope to explore this or anything you can comment about that.
Yes, so there's definitely a lot of directions for exploration in terms of the state representation. So regarding using the domain object state. So we didn't want to come up with any representation that would tie us to the language of the domain. So we didn't want a domain-specific representation of the state, like how many tracks are there, are the packages far from the tracks. But having said that, so yes, there's a lot of still domain-independent things that you could put in your state representation. So for example, the how long have we been stuck at the same heuristic value, or how many states do we have in the open list, or what's the distribution of the heuristic value in the open list? Are all the states the same with respect to the heuristic value, which is intuitively not too good? So there's a lot of more that we can include in the state representation, but we quite intentionally steer away from domain-specific features there.
All right, one more.
Thank you. If I understood correctly, when you switch from one search routine to another, you keep the open list from the previous one, right?
Yes.
Do you reorder the nodes in the open list according to the new procedure that you go with?
No. So there's only one global open list, and there's only one heuristic function, so the ordering never has to change. So the interesting bits is when you do local search, for example, when you start doing it, like you merge your local list into the global one. But otherwise you operate with just one open list.
Well, if you started with a local search and then you switch to a GBFS, then your open list is not ordered by the GBFS order, right? But
GP
the best first search.
Depth first search. So we've got depth first. We've got local search, We've got random walks, which just follow every expansion with a random walk, so it's not the problem there. The only two subroutines that require ad hoc data structures, local data structures, are local search, and we just merge the list into the global one at the end of this. And the same is the case for depth-first search, with the exception that for depth-first search we actually have a stack rather than a queue.
All right, let's thank the speaker one more time.
We can take it offline. Thank you.
All right, so our final talk, this is a short talk, is size-independent neural network transfer for RDDL domains, and Sankalp Garg is going to give the talk.
Thanks for introducing. So I'm Sankalp, junior undergraduate at RDDL India. So this is joint work with Aniket Bajpai and Professor Mosam. So let me just start by telling a little bit about RDDL. So RDDL is a representation for the factored MDPs. It's a symbolic representation, and the main components of these are the fluents, the state fluents, which change over time, the state non-fluents, which do not change over time, and the action predicates, which are defined over the objects. So for example, in the sysadmin domain, the goal is to keep as many computers alive as possible. So the on and off state of the computers are the fluents. The connection between the computers are the non-fluents, as it doesn't change. And the action of rebooting over the computers is the action fluent. So the research challenge. So we asked the question that what is the power of deep learning in the symbolic domains? So a little bit difference between the modern probabilistic planners and the deep reinforcement learning planning. So the modern probabilistic planners, like the PROST, they actually look ahead into the states, they expand the states and then plan at every step. They expand the states and plan at every step. While the deep reinforcement learning planners, they plan during the training time, but during the execution, they just look at the state and compute a policy and then directly execute. So planners like PROST, they can't do anything offline, so they interleave planning and execution. But so there is no natural way of transferring across problems. So every time they have to compute a new strategy for every different problem instance. So if you have a problem of size, say 10, and you give it a new problem of size 50, then it computes the policy again. While the deep reinforcement learning planners, they actually compute a representation. So you can actually learn a policy for a small size domain and transfer it over a large size. So we answered the problem that we can use deep learning for transferring across problem sizes. So we call a network as TrapsNet, a network that can transfer across the problem sizes. So the setup is as such that we have got small size problems which are represented as the graphs. We train a model TrapsNet, which outputs a generalized policy. Finally, during the test time, we have a very large problem instance, and we use the generalized policy without any other update to get the reward. There are certain assumptions which we have in our domain. So we assume that we have only unary fluents, unary action templates, and unary non-fluents, except one binary non-fluent. So the binary non-fluent will be used to represent the graph. These are actually satisfied by a lot of problems. So for example, this is admin domain, the game of life, academic advising, skill teaching, etc. So I'll tell a little bit about the framework. So our state is represented as a graph. As you can see, the edges in the graph are directed, and they are represented by the non-fluents in the RDDL domain. The nodes are the objects. Every object will have a feature which will be taken from the RDDL file. The feature will be the unary fluents and the non-fluents. We use a graph embedding method, in our case, the graph attention networks. So I'll briefly talk about the graph attention. So every graph embedding method has a network update so that it removes the edges and gets an embedding for each of the nodes. So this removes the need for any edges in computation for the graph. So it'll be difficult to explain everything about the GAT. You can think of it as removing the graphs, and for every node, it captures the neighborhood information into one node embedding. After we get the node embeddings for each of the nodes in the graph, we pool the node embeddings to get a red embedding, as you can see, which we call as the state embedding. The state embedding will have every information for the state which we are in right now. We concatenate the state embedding to the node embedding. So now every node will have a local embedding value which will represent the local information, and the state embedding which will represent the global information. We finally take this local and the global embeddings and use a fully connected network to output a policy. So as you can see, for every node, we run it through the same fully connected network to output a score. So for every node in the graph, we have a score. We normalize the score using the softmax, and this gives us a policy. So we select the action which has the highest probability. So the experimental settings, we train our policy on the small size domains. You can train it on 1 or 2 or 3 problems. We train it on 2 problems. So for example, in the sysadmin domain, the number of nodes we train on are 10, and we test it on 50. So the number of states are exponential in size. So we train it on 2 raised to the power 10 states and test it on 2 raised to the power 50 states. And we test it on 3 domains. So the results shown on the instance 9 of the RDDL. The green one is our final transfer architecture. As you can see, at time t equal to 0, it directly outperforms all other methods. It even continues to stay better till the end of time. So even after 6 hours of training, the RL methods can't reach the performance which is done by this network at the transfer time. So we are actually not the first ones to use the neural networks for planning. So previously, these methods have been used, and we had a previous paper at the NeurIPS also. But the constraints in the previous NeurIPS paper was that it couldn't transfer across the problem sizes. So the problem size had to remain constant, but the graph structure could change. So in conclusion, we give a generalized policy for every domain, and the method continues to remain better when trained from scratch. So the future work involves removing those constraints of unary fluent and the non-fluents, and hope that it can solve every MDP problem in the RDDL domain. Thanks. Questions?
All right, we have time for a few questions. Wait, so.
Okay, thanks. That's great work. So you generalize across objects, basically through max pooling.
Yeah.
Right. Are there better ways? Are there better ways to combine all the information from multiple objects? Like, could you use attention, self-attention there to combine the info?
Yeah. So we had to make it fast. So we actually tried it only max pooling and mean pooling. But you can actually use other methods like the RGCN or any LSTM method. But the problem with that is that it has to have a sequential order to pool. So right now, we don't know any method which is non-sequential in nature. So if I take object 1 and 2, which will be different from object 2 and 1, if I pull it using an LSTM or other way. So I need something which is non-sequential as well as which preserves the embedding size.
Okay.
Hi. So two questions. First, is there a reason that you have chosen exactly these 3 or 4 domains that you have showed in your evaluation? And then the second one, is your approach better for some type of domains, or on what type of domains does your approach work really well, and are there also types of domains where it does work not so well?
Yeah, so by the time we were doing this work, so these are the 3 major domains which satisfy these constraints. We have one more domain, the skill teaching, but at the time of publishing the paper, we didn't have the results for that. We actually have managed to solve every MDP problem which we have submitted to NeurIPS this time. For the, what was the second question I forgot? It actually works well on every domain which satisfies these constraints. So for the new method, out of 12 RDDL problems, we are able to solve 10, but right now with these constraints, we are able to solve every problem given in the IPPC.
One more quick question.
So if I understood correctly, you have compared with reinforcement learning methods, but what about probabilistic planning methods?
Yeah, so as I mentioned that it's not fair to compare with, I'll show a slide. So it's not fair to compare with planners like PROST because they are online. So our method is offline, so we can't compare with PROST. But even if you want to look at the results for the PROST, so you can see that in these domains, this is admin and the game of life, we are pretty close to the PROST at time t equal to 0. This is the PROST results as given in the paper and on the repository. Even on the academic advertising, we outperform the PROST at time t equal to 0. So without any computation so these are all trained on a small instance of 1. And for testing on 9, so without any computation, we outperform the PROST at time t equal to 0. But yeah, it's not fair to compare.
All right, let's thank the speaker again and get coffee.